If you enjoy Astronomy FM radio, please let us know with a small donation. We do rely on your support, and it's true. Every little bit counts.
AFM.
Gentlemen, we have a serious problem. The Limeys are taking over Astronomy.fm.
Welcome to Under British Skies. News, views and interviews from the UK world of astronomy with Richie Jarvis, Nick Howes, Ian Melville, Paul Harper, Nick Evitts, Sam Hawkins and Jenny Winder. The show is engineered by Michael Forster and produced by the team. Previous episodes of Under British Skies are available to download from iTunes. You can contact the team on Twitter at Under British Sky or email us at ubs@astronomy.fm.
Good evening and welcome to Under British Skies. Sorry we can't be with you live tonight, but we've put together a nice show for you anyway, so I hope you enjoy it. With me this evening is Nick Evitts. Good evening, Nick.
Good evening, everybody.
Right, so I'm not sure whether we need to do the introductions anymore. In fact, let us know. Do we still need to do the introductions anymore? Please email into ubs@astronomy.fm with your comments on that one. Right, so this evening we've got an absolutely packed show for you. As usual, we've spent a bit of time putting it together, and I hope you enjoy it. Anything to add, Nick?
Actually, it's a brilliant lineup. Ian's interview with Dr. Simon Green is absolutely terrific. I've met the guy in real life, and he is really, really good at explaining robotic missions and why they are so good, and getting into the actual science that they do and how they work. So this is a really brilliant piece of information that he's going to give us tonight.
Yes, it is a fascinating, look into the world of NEOs. In fact, I was trying to think of a suitably NEO-related title for the show this evening, Nick. So if you can think of anything.
Yeah, I'll get the old thinking cap on. But actually, the timing of the interview with Dr. Simon Green is very, very good, because one of the big news items, certainly this side of the Atlantic, is the fact that the government is putting an extra 60 million quid into space. And they've also increased the subscription paid to the European Space Agency. And there's already spin-offs coming our way, which is fantastic news for British employment. Well, it's even better for Oxfordshire, because they're getting a European Technical Centre. It's going to be around telecoms, and they will be producing the next generation of transmitters and receivers that will be used not only on space probes but on ground stations. And it's going to bring in quite a large number of the world's top players, just to see what's being looked at, look at the concepts, and looking for everyday uses here on Earth. So this to me is the best thing about space exploration. Yes, it's focused outwards, but the spin-offs inwards are always well worth having. Teflon Pan spin-off from the American space program.
Anyway, let's have a look at the news, shall we?
Yep.
And what's Jenny given us this evening?
Well, Jenny's, of course, one of the big stories is, of course, the extra 60 million quid being invested in UK space. And the other thing is they've upped the subscription the UK government puts into ESA, which means for Brits, it means jobs, it means a technical centre in the UK, and it's going to mean an awful lot of big companies wanting to suddenly put places into this country purely because of the research that's going to be done here. The really great thing is the UK government is also investing more into the European Space Agency. It has upped its subscription, which is good for the United Kingdom because it means jobs. Oxfordshire is set to see an ESA technical centre going in there, which is going to be for telecoms, and it's going to pull in an awful lot of the world's big players because they're going to be looking to have a base there too, purely because of the work that's been done at ESA.
Yeah, I think looking at this, it's going to be really nice to get a centre, an ESA centre in the UK. I mean, if you think about it at the moment, if you want to go and work in space and you want to go and out of satellite work, you've pretty much got to go over to the continent, which is not good for any of us, really. It'd be much better to build ourselves a good base here in the UK and attract that sort of mindset into the UK as well.
Absolutely. And of course, the two main centres on the continent is either Darmstadt in Germany, which is where most of the control work is done, or it's in Holland at ESTEC. So having one even closer on our doorstep means that we're going to be literally at the cutting edge of telecom technology.
Exactly. Anyway, moving on, we've got there's been a study recently into the effects of microgravity on astronauts, and basically looking at a comparison between what microgravity does to the astronaut's body against what old age does to your body. To actually look at it and see and see what's going on. So what they're going to be doing is putting 12 volunteers to spend 21 days in bed. I think they could get pretty boring. They will lie for 24 hours a day with their heads tilted 6 degrees below the horizon. They will not be allowed to get up for any reason, not even a breath of fresh air. Changes 21 days. That sounds like hell, actually.
You can read books, you can watch DVDs, you can use your computer. But yeah, I understand why they're doing it. It's the closest thing they can get to a microgravity environment without using expensive planes and crazy manoeuvres.
But surely they have 6 people on the ISS at any one time at the moment. Surely that is enough of a enough of a sample to be able to measure what happens to the human body in microgravity. And they're up there for 3 or 4 months, some of them.
Yeah, but the problem is you haven't got them in one position or one place consistently. If you're an astronaut on the ISS, your day is fairly well filled and you're in motion all the time. Whereas these guys are going to be fairly static. You probably be allowed to move in the bed and that's about it. So again, you can also monitor them better and probably better than you can, say, on the space station. The doctors and the physicians and everything else are actually there. They can see exactly what's happening instantly. And they can also wire you up much better than you can if you're on the ISS. Because basically bandwidth is limited on the ISS. I hear the internet is actually quite slow up there. So trying to wire a guy 100% and constantly monitor it would probably be very difficult. But in a bed, in a hospital room, easy, if you'll pardon the pun.
Yes, I know what you mean. Okay, well, I do. It does make me wonder. It makes me wonder whether it's necessary to do that. I mean, you could, what are they actually trying to measure? If somebody's in, the whole point of this is that somebody's in microgravity. It doesn't matter if they're working or not. They're going to lose the same amount of bone density, aren't they?
Yep, there's the risk of kidney stones, demineralization of the bones, which pushes that risk up, and it alters the ability of bones to heal after fractures. Muscle mass is lost, strength and endurance goes, fatigue and injury goes up, and of course the heart is also affected. Diminished cardiac function and possible disturbances in heart rhythm. And it's better, I think, if you're going to do that down here, where you can have a crash team right there, than trying to do this on the ISS, where basically you can't get a crash cart up there fast enough. And I don't think I don't personally know, but I wouldn't believe they would have that type of kit that's floating around all the time anyway. And there's probably just one person.
But hasn't the jump by Felix Baumgartner last month told us that basically all you need is some sort of propellant to get you into the top of the atmosphere, away from the ISS, and surely you can then survive a free fall back into the atmosphere.
It was a great experiment, but a lot of that was aimed at finding a method to get astronauts or cosmonauts out of a capsule that's in trouble as it's going up.
Yeah,
that was the whole
but
point.
There's no reason why there's no reason why they couldn't now say, okay, well, what we're going to do is we're going to design an emergency jettison buoy or whatever that gets used as part of the regular space station, but then in the event of an emergency, you can just detach this thing and drop it into the atmosphere.
The big problem is, of course, is going to be how many do you build? You need to put quite a few up there. You need a launch system to get it there in the first place. We don't have the launch capabilities we had, say, in the 60s and the 70s.
No, we've got the Ariane series. Ariane series can carry a hell of a weight up there.
Oh yeah, it can carry a hell of a weight up there, but it's getting their technology built. You got to build a small one-man capsule that can survive re-entry.
Yeah,
and most of the time,
that's exactly what Felix Baumgartner just proved that was 100% feasible by jumping from such a high platform.
But I don't think you can jump safely from the ISS back.
Why not?
You need a capsule. You have to go through re-entry properly because it's in low Earth orbit. It's beyond the atmosphere. He didn't.
Yeah, Felix Baumgartner was beyond how much of the 95% of the atmosphere.
But he didn't have to do re-entry.
Yes, he did. He came in on the atmosphere, and if you remember, he was spinning as he came down because there was not enough atmosphere for him to push against to be able to guide himself down, right?
But the thing is, stuff that's coming in from from low Earth orbit burns up. He didn't burn. He wasn't all the way out there on the edge of space.
Yeah, but he was high enough. I'm talking about the fact you can quite easily drop something into the atmosphere.
But it's still go through.
So tell me why he didn't burn up.
Because he wasn't actually re-entering as a space capsule would.
He was re-entering. He had
a supersonic.
He was coming through the atmosphere for the first part of his fall. There was no friction against his suit, pretty much.
Yeah, he was still inside the atmospheric envelope. He wasn't in low Earth orbit because he went up in a balloon gondola, and a balloon can't get beyond the atmosphere.
But surely, if you launch something from the ISS and you basically start an immediate braking maneuver, it's just going to fall inwards at a controlled rate.
But you still need a heat shield to get yourself inside the atmospheric envelope.
Why?
Because you still be at the speed it's going to be going.
No, but it's not going to be going relative to the atmosphere. It's not going to be going at any speed.
And as I say, the way I understood it, he didn't actually re-enter. He wasn't actually out in space.
No, he wasn't in space. That's not what I'm saying. I'm not saying he was in space. I'm saying he was outside most of the atmosphere. And because he was outside most of the atmosphere, basically, if you've got something in orbit, right, and it's in a low Earth orbit, and it's traveling around the Earth at a certain height, let's say 35 kilometers.
Yeah.
Right. I mean, what height's the ISS at? 235, something like that?
ISS height. Let me just check that out. Let me look that up because the way I understand it, it is beyond atmospheric drags. Therefore. Right.
It's 370 kilometers up. Okay.
Yeah.
So that's the orbit height of the ISS.
That is further than he is. That is.
Absolutely.
He didn't go that high.
Felix Baumgartner, he jumped from 39 kilometers. Right. So there's a huge difference. So if you treat him as being in orbit at a height of 39 kilometers, which is essentially what he was, right?
Okay, but as I say, I still don't think he was actually physically re-entering the atmosphere.
No. Just hang on a minute. Look at this, right? So he's orbiting at 39 kilometers, right? Because he's going around at exactly the same speed as the body he left.
Okay, I'm listening. Yeah.
Plus or minus wind. Right?
Okay.
So 39 kilometers. Now increase it to, let's say he could. He couldn't. He went as high as he could with that balloon, right? But let's say you could get something to take you up from the surface of the Earth to, let's say, 60 kilometers.
Okay. The figure I have here for the
ISS height is 320.
350 kilometers.
Yeah, we'll get to that in a minute, right? I know there's a big difference between 39 and 350. That's not the point I'm trying to make. The point I'm trying to make is that the ISS is traveling, to maintain that orbit, is traveling significantly faster.
Mm-hmm.
Right? So if you want something to come in, right, if you break that, instead of coming in and sort of like diving through the atmosphere like the shuttle did,
mm-hmm.
if you actually just perform a braking maneuver to slow yourself down, your orbit will come inwards, yeah?
Okay, so you're thinking something like aerobraking?
No, not aerobraking. You don't need aerobraking. You basically just fire a rocket.
Okay, so basically, so scenario is something like a Gemini capsule, coming back in. They fired a rocket, the engines, and it came back in the atmosphere.
Yeah, and as soon as it comes back into the atmosphere, then as soon as you get down to a particular altitude, and Felix Baumgarten was above that particular point because there was virtually nothing there where he was jumping from.
Okay. I think so. The only thing I can think, the only problem I would have doing it that way was if it's a casualty, he would.
But that's why I'm saying a capsule instead of just a spacesuit.
Yeah, it would have to be a capsule because at some point there will be stresses on it.
Mm. Yep.
And as I say, I think the whole idea behind his jump was they were trying to figure out what was the minimum requirement support-wise to successfully parachute from that altitude.
Yes. Oh, yeah. But the whole point is that if you can do it with a guy in a suit, you can do it in a small capsule, a one-person capsule.
It's an idea. I'm pretty, and I don't think it's ever been seriously thought about by the space agencies, because most of the current thinking is if we need to get people back home in a hurry, we stuff them into, for instance, the coming technology is the Orion crew capsule.
Yes.
Stuff them in one of those, re-enter the atmosphere traditionally, parachute and recover from the sea.
Mm.
I suppose if you could find a material strong enough to survive, and that could deal. See, that's the problem. I still think there's going to be some form of re-entry involved, coming from the space station. Maybe that's the problem because I'm looking at this in a classical frame.
Yes, you're not thinking outside the box.
No, this one, no. But yeah, maybe you. Yeah, say I'm just thinking. Okay, how do I get somebody from a damaged space station to home alive? And most of I'm thinking
in the quickest possible fashion.
Yeah. And frequently that involves a heck of a re-entry maneuver and an ablative shield at least. But I suppose it could be possible.
Well, it would be interesting. Anyway, should we get on with the news?
Yes.
After our little segue.
Isn't this good fun, though?
Right, so we've also got the European Space Solutions event on the 3rd to the 5th of December 2012. So that's the UK Space Agency is hosting the biggest EU space event this year, it says on their website. And of course we're not going.
Yeah, it's always the way, isn't it?
Yes. David Willits MP, European Commission Vice President Antonio Tajani, and Sir Richard Branson will focus on the framework for ensuring growth in the space sector.
It's to see Branson going.
Yes, Branson's going. Yeah,
it's good and all. A lot of my problem is I'm used to the idea of a national group, the national organisation running space, government runs space.
That's because you've been in the US too long.
Well, we had our stint at it, but a government under a certain politician shut us down before we could even prove its worth, which is a big. I'm sure you know what I'm referring to, Richie. The Black Knight rocket. We had the perfect launch platform. We had a great position in Australia to do it from, and the government.
We could have been ahead of that race and beaten the Russians and the US.
We could have been raking it in the satellite launch business and.
But you know, I mean, if you think about it, the UK or the British jet industry went the same way.
Yes, we gave the Americans the jet engine. So Frank Whittle's invention. You try finding a book over there that agrees with that fact.
I bet they invented it all themselves, didn't they?
It's like the Harrier jump jet, the AV-8 as it's called in America.
Yeah.
I had to tell. I was talking to a Marine who was flying one. And said, hey, this is a great American aircraft. He says, no, that's a British aircraft, actually. Built under license from Hawker Siddeley. No, it's American. It's built by an American company. No, they're building it under license, old boy. It's a British design. And I showed him a page showing the original Harriers.
Yeah.
Oh, you could hear his jaw hit the floor. But as I say, it's like everything else. It's the national. A lot of other countries are just as guilty of it. About if this has been done, it must be ours.
Yes. Yeah.
So it's not just the Americans, and I'm not trying to knock America about this. In all honesty, it happens because you get a mindset, and I've seen it over here in England and Great Britain too.
Right, we better get on with this now. So let's rattle through the rest of the news. Right, so what else have we got to look at? So the maths that made Voyager possible. So NASA has been telling everybody about their exploits at the edge of the solar system. Ah, right, okay. It was only possible because of some clever maths and the persistence of a PhD student who worked out how to slingshot the probes into deep space.
Guess what they got told to tell the story, Richie?
Yes.
Horizon, the BBC. But no, if you can find this show on the internet or download it from iPlayer, watch it. It is brilliant. And to watch a young Carl Sagan in his element, how this guy dealt with all the issues and potential disasters about the Voyager mission is brilliant. He's cool, he's calm, he's collected. It was just brilliant, and I'm pretty sure he didn't realize that a lot of the time the news cameras were actually recording how he was reacting to news. Oh, we got a problem with one of the Voyager probes. It may not do its job. He took it in his stride, and he just kept going. And the rest, as they say, is history. Pale blue dot, Cosmos, all history. But it just shows you that when something's done right, by gum, it's done right. The thing is, and people forget that, and that we're
the Voyager probes. The Voyager probes. I mean, they were launched before I was born, so. But I've heard about them all of my life, and I wish them well. I mean, they're doing a great job still, aren't they?
Yes, Voyager 2 is still reporting home. Every now and again, they have to shut off another experiment to power the transmitters so they can get the vital science data back.
Oh, actually, no. I was 5 when those launched. 1977 they launched.
Yeah.
I was alive.
I was 1977, 1973 was 10 years. So I was 15 odd when they were launched. And I remember everybody being in awe. Transistor technology really showed its mettle, and it's still doing it. It's still running. And everybody talks about, look at the amount of circuits inside my cell phone. Guess what? The technology that built your cell phone is out there at the edge of the solar system right now. It's all miniaturized.
Yeah, it's amazing. It's amazing to think that they're still going. I mean, that's what gets me, the fact that they've got enough fuel to survive till 2020. That's just incredible. But
They pioneered the atomics, the snap batteries, which are used in a lot more space missions. They proved them to be safe. They proved they could be launched without risk to humans. Go Voyager, go!
And of course we've got the Leonids this month as well. The residue from Comet Temple Tuttle, which is peaking tonight. So you might on the night this is going out on the Sunday. If it's clear, you should still see a few meteors out there. We hope. But I don't know about you, Nick, but it's cloudy where I am.
It's been cloudy for the last 72 hours. I can see a very hazy moon. I want to know who's just been buying astronomical equipment in my area because I want to word with him. He bought my meteor shower.
Yes, somebody needs to pay for our lousy weather.
Patrick Moore in there too. They're wonderful chap he is.
On with the interviews, I think. So you've had a listen to the first one. I had a listen to the first one. Very, very good interview Ian put together here. Really enjoyed it. But we've Ian split it into two parts. So first of all, we're going to go over to Dr. Simon Green, the Senior Lecturer of Planetary and Space Sciences at the Open University. Take it away, Ian.
Well, good evening, everyone, and welcome to this month's edition of Under British Skies. I'm very pleased to welcome to our show Dr. Simon Green, who is Senior Lecturer in Planetary and Space Sciences at the Open University. Good evening, Simon.
Good evening.
And we're going to talk a bit tonight about some of the projects that you've been working on, but first let's start with a little bit about you. What's your background in astronomy?
Well, I do research into small bodies in the solar system, that's asteroids, comets, interplanetary dust, through space missions and ground-based observations and laboratory modelling.
Okay, and what sort of projects have you worked on?
Well, I started after my first degree in astronomy, which was at St Andrews, and I went to the University of Leicester to do a PhD studying asteroids, but I used a satellite that was actually an infrared astronomy satellite called IRAS. This was in the early 1980s, and it was designed to do an all-sky survey of the infrared sky, and it scanned the sky multiple times and used the multiple observations to remove moving, false sources, noise, and so on. And any object that was confirmed in subsequent orbits and scans as a point source was put into the catalogue. And my supervisor at Leicester, Jack Meadows, had the idea of searching among all the sources that were basically rejected from the survey to see if there were asteroids present. And we found a few asteroids, but actually we're much better at finding comets, and discovered 6 comets, including IRAS-Araki-Alcock, which came extremely close to the Earth and was visible to the naked eye.
Was that code discovered by George Alcock, by any chance?
Yes, independently, yeah. But because we were using a satellite and I was a mere research student, those people in charge of the survey essentially didn't trust us to announce any discoveries, and we had to get them confirmed by ground-based observations. So although we found the object first, it wasn't confirmed until after it was independently discovered by a Japanese astronomer and George Alcock on the same night, essentially. Our confirmation came afterwards, and so although we saw it first, it was called IRAS-Araki-Alcock after the satellite rather than me, unfortunately.
And was that were the comets easier to see because they were faster moving?
No, it was more because they contain a large amount of dust that's dragged off the cometary nucleus when they come close to the sun and the ices evaporate, and dust is very efficient at radiating at infrared wavelengths, which is what we were using. So it's basically looking at the heat from heated dust grains. And because these dust grains are fairly small, they absorb sunlight, but they find it quite difficult to radiate longer wavelengths because the wavelengths are comparable with the size of the dust grains. And so they get very hot. And so in the end, they actually radiate at higher temperatures than they should. And with the large amount of dust surrounding the comet in dust coma, they appear to be much brighter than a small asteroid passing close to the Earth would do. So we were actually more efficient at detecting those and found them. And we also found the very first example of what are called cometary dust trails, which are larger dust particles which trail behind and somewhat in front of a comet in its orbit. And these are the millimetre and larger size grains which are not dragged very far away from the comet, and so they track in its orbit. And eventually, of course, these end up forming meteor streams.
Oh, all right. Well, that's a very interesting result. So that was basically the first mission that you worked on, but you've done quite a few since then, haven't you?
Well, that PhD project fortunately the end of it coincided with the arrival of Comet Halley, and I was very lucky and got a job as Comet Halley coordinator for the UK, which essentially meant trying to mobilise the solar system community to cooperate over observations. And I moved to the University of Kent, where they ran an experiment on the Giotto spacecraft, dust detection experiment. And so I was doing ground-based support for that experiment and also analysing the data. So that really got me into a career in astronomy through working on contracts initially and then as a university lecturer.
Well, that's interesting. So tell us a bit about this dust detection mechanism on Giotto. How did it work?
Yes, well, the Giotto spacecraft flew past Comet Halley at very high speed because Halley is one of those comets which orbits the Sun more or less the wrong way. And so if you launch a spacecraft from the Earth, it has the Earth's orbital speed. And so when it arrives at the comet is orbiting in the opposite direction, and so you end up with a relative speed of more or less twice, actually somewhat more than twice the Earth's orbital speed. So the spacecraft arrived at Comet Halley, the flyby, at 68 kilometers per second. The Earth's orbital speed is about 30. Now, at those very high speeds, dust particles can do an enormous amount of damage. So you have to protect it in some way, and that was done with something called a Whipple bumper shield, which essentially had two thin layers. The first thin layer, when hit by a particle, caused the particle to vaporize. It could penetrate that front shield, but the ejector, the damage, if you like, that was caused, would spread out and hit the second shield over a much larger area, and therefore, with a relatively light weight, you could protect the spacecraft from relatively large particles. Now, our experiment put a sensitive microphone on that front shield, and when a particle hit, it would cause the shield to vibrate, and you could measure those tiny vibrations. And it used a piezoelectric sensor, so it's exactly the same kind of thing as you have in a lighter, where you have these little electronic things, have a crystal which you compress by pressing the button, and it produces a voltage which produces the spark, and you light your cooker. But in our case, tiny voltage, would be measured by amplifiers and the experiment. So we could measure the impacts of particles on the whole of the front shield of the spacecraft and work out the amount of dust that was present in the comet as we flew past.
Oh, right. Okay. So were the results from that as expected, or?
Well, generally, yes, they were. Because of the very high speed and the way the detector was designed, we had a very small data rate from the spacecraft. And so we could only count particles over a timescale of about a second. So, of course, over a second, the spacecraft had traveled 68 kilometers. And so we basically, each time we got a signal of the number of impacts, it was averaged over 68 kilometers. And what you'd expect to see is as the spacecraft approached the comet, you get a few impacts, and then gradually the impact rate would rise. And then the closest approach, it would reach its peak, and then it would fall away again. And that's what happened. Of course, Giotto was designed to fly as close as possible to the comet, and there was no guarantee that it was going to survive the close encounter. In fact, its nominal end of mission was the closest approach. In fact, the spacecraft was quite severely damaged. The camera was destroyed and other sensors were damaged too, but it survived. And we got measurements on the way out too.
Right, so that's because of the high speed of the spacecraft. I believe you worked on another cometary mission more recently. Do you want to tell us about Stardust?
Yes, the Stardust spacecraft, my involvement in that came about because of the experiment on Giotto. Stardust is a NASA mission, a discovery mission. It had the rather daunting task of collecting samples from a comet and bringing them back to the Earth, something that Europe has been trying to do for a long time and essentially determined that it was too expensive. And their comet mission, which is flying now, about to arrive in a year or so's time at a comet, and it's going to land on a comet and take samples of the surface but do experiments in situ on the comet because it's too expensive to bring the sample back. Now, Stardust, which in space mission terms is a relatively cheap mission, about $250 million, essentially sidestepped the necessity of landing on the comet and the difficulties that's involved, and it just flew past. But what it essentially did was stuck out an arm with a collector on board and let the particles hit it, and collected the particles, put them back in a capsule and returned them to the Earth. And of course, the trick there was to be able to slow the particles down gradually enough so they weren't destroyed. There were some simple experiments on the spacecraft. One of them was a dust detector on the front shield. But because of our experience with Giotto, we were asked to add some extra sensors that used a larger area of the front shield to measure the big particles. Because the spacecraft, unlike Giotto, had to survive because it had to bring the samples back. And so there was quite a debate among the astronomers who wanted to go as close as possible to the comet to collect as many particles as they could, and the engineers who were responsible for the spacecraft safety who wanted to go as far away as possible, so they didn't risk being that small probability of being hit by a big particle that would destroy the spacecraft.
Must have been some interesting meetings in that one.
And actually, for some time we were in an impasse because there was a sort of safety requirement, if you like. There's always a probability that you get hit by a big one, but that probability had to be low, a few percent. And that essentially, if you modelled what you thought the dust production from the comet would be, placed a minimum distance at which you had to fly. We also had a target for the number of particles we wanted to collect. And of course, for every big particle, there are more small ones and more smaller ones. And so we had a target of collecting 1,000 particles of 15 microns in size or bigger. But of course, if you had 1,000 particles of 15 microns, then that might mean the biggest one might be a few millimeters or it might be a few centimeters, depending on the distribution of sizes. And our experience with Giotto meant that when I came onto the project and I said, well, if we see the same size distribution as Giotto, then in order to avoid having big particles where Giotto detected a lot, we had to fly more than 600 kilometers away, and then we wouldn't detect enough small ones. So we were in a real quandary. In the end, we sort of came to a compromise and targeted at 300. That would give us a good chance of getting the 1,000 particles, but we had to take a bigger risk on the spacecraft safety.
300 kilometers, that's pretty close, isn't it?
Well, remember the comet is only a few kilometers in diameter. The Bill 2, which was the target, it was about 6 kilometers across. And that object, it was not a hugely active comet, so the amount of dust it produced was a lot less than a Comet Halley, but of course we were going twice as close. As it turned out, there's a big error on the trajectory of the spacecraft too, and so we ended up going rather closer than that, about 250 kilometers in the end. So we were fairly close to the point where there was a good chance of being hit by a very big particle, and certainly on Stardust, it's basically the same idea of having a shield on the front with the detectors on it, on the front shield. And we also had a detector on the shield behind, so that if any particles penetrated, we could measure those. And we got, I think there were 7 penetrations of the front shield in that encounter. And the largest particle that hit the spacecraft, which didn't hit our experiment, but we can work it out from the size distribution, was about 4 millimeters. 1 centimeter would have destroyed the spacecraft, so we were getting a bit close.
Yeah, that is close, yeah. And so this sample was returned to the Earth, wasn't it? And how much material was actually collected?
An astonishingly huge amount of 4 milligrams.
Wow.
Particles, and that sounds really a tiny, tiny amount. You know, you sort of you could fit all that mass on a pinhead. Now, at the time when the mission was first proposed in the 1980s, in fact, the people who were proposing the mission had about 7 different tries at trying to get it selected. If they'd been successful the first time round, what they would have done is they had a big science team who would have put all these particles together in one little pot and said, which experiment are we going to do? Because they would have needed all the mass. Nowadays, laboratory instruments are so sophisticated that we take an individual grain that may be a few microns across, and we slice it up into pieces and give those pieces to different groups, each to do their own experiments. It's quite astonishing. And this is why bringing a sample back is so valuable compared with doing experiments actually on the comet.
Do you know how much of it is left?
Oh, more than half. Some of it's trapped in the material. The way that it was collected was with a material called aerogel. It's a very low density, essentially like a glass sponge, if you like, but a density of about 1,000 times less than solid glass. And the idea is that the particle hits this very low density material and punches its way in, and is slowed down gradually. So the heat that's generated from the original speed of the particle isn't so great that it vaporizes the particle. The particle is still damaged. It tends to have a fusion crust on the outside, but reasonably robust particles can survive this collection process. And so you can cut them up and get into the inside and see what the cometary particles are made of. And that was where the real big surprise for that mission came, because the reason why we're interested in comets is because they formed in the outer reaches of the solar system, where beyond what's called the snow line, where water ice and other volatile gases can condense. And they're made up of a significant fraction of water and other ices, together with dust grains embedded in them. And the belief is that a significant number of those dust grains, which we were detecting, may have the composition of the original material that was present at the beginning of the solar system, because we know it hasn't been heated significantly, because the ices would have melted and the comet wouldn't be there anymore. But also may contain particles that predate the solar system. So these are surviving interstellar dust grains from the early history of the solar system that weren't vaporized themselves by the sun forming. So we were expecting to see particles which gave us a view of what the outer solar system was like 4.5 billion years ago, and some particles that predated that. What we actually found was that all the really solid particles, the ones that survived intact in the aerogel, turned out to be very high temperature minerals that must have formed very close to the sun. And that sort of gave a problem for those people looking at models of how the solar system works, because you have to make a comet out of material ices that are a long way from the sun, but somehow they've got to contain dust grains that formed very close to the sun. And so those dust grains have to basically get from near the sun to the outer edge of the solar system. You have to have a mechanism which shifts these grains from very close to the sun to a long way away, but without mixing everything else up as well. And that's placed quite serious constraints on our models of how the solar system formed. So in that sense, Stardust was very successful. Now, it may be that there are those primitive particles present in the dust from Comet Field 2, but primitive things we expect to be very fragile. And so maybe they're the things that when they hit the aerogel, even though the aerogel was a gentle deceleration, it may have still been too much for their survival. Because we see many tracks of particles in the aerogel where basically they look like a sort of big bulbous shaped track with no particles at the end, basically just disintegrated. The material is still there, of course, it's stuck in the material around the aerogel, but it's much harder to interpret because you don't see the original particles, you're seeing the sort of the residue of the impact.
All right, well, that's a fascinating result. I mean, it's really good when we have these results which we're not expecting.
Well, if you ask anybody who's worked on space missions what they expect, and what they'll say is, I expect to be surprised.
Yeah.
You always find something that you didn't predict. And in a way that's great, because if you saw everything you predicted, you kind of feel like it was, not entirely necessary to go there. But we always find things that are unexpected. And in a way that's why bringing samples back is so important, because if you do an in situ mission, obviously if you're going to see an object for the first time, then you can learn a lot from the imaging and the spectroscopy that you do of the object close up, where you can see the details of the surface, which we can't from the Earth. But if you want to do really in-depth studies of the chemistry and the evolution of the body, you need to have experiments to work on samples. Now, here's the problem, because if you're taking a spacecraft to the target with the experiments on board, you have to be sure that experiment will work, so you have to play safe and design something which you really understand how it works, you know it's going to be reliable. You have to anticipate what you're going to find, so the experiment asks the question that you want to ask. You can't sort of go there and say, yes, we found that, let's try this, because you've got to decide what you're going to try before you launch. And of course, you launch, and it may be 10 years between the launch date and the arrival at the object. So your experiment is 10 years out of date because of that, but actually it may be even more than that, because you probably had to design your instrument 5 years before the launch in order to build it to put it on the spacecraft. So your experiment may be 15 years out of date, and you may be asking the wrong question.
Yes, that's why sample return missions are so important.
Yeah, and the problem, of course, is that they're very difficult, because if you want to go to a target, if you want to fly past, basically all you have to do is launch from the Earth and get to the target. The next most difficult thing is to rendezvous. So you have to go there, but you have to carry extra fuel to allow you to decelerate when you get there. and match speeds with it. If you want to land, then you have to have a mechanism for landing and more complicated mechanisms on the spacecraft. You need to take a sample, and then you've got to come back, which means you've got to launch back off the body, and you've got to fly back to the Earth. All that mass to do that has to be launched on the rocket in the first place. Of course, it makes the missions much more complicated and much more expensive.
Yeah. Tell us a little bit about Marco Polo R.
Well, Marco Polo R stands for, well, we're not quite sure, revisited, revived, could be anything. It came about from a previous mission called Marco Polo, which was originally planned to be a joint European-Japanese mission. That was the way we could afford to do a sample return. And it was going to be a Japanese follow-up to Hayabusa. That didn't really work out because of the delays in their program, and the timescales didn't quite match. And so we tried to go alone. We were selected out of about 50 mission proposals down to the last 4. We did an industrial study, and the mission was entirely feasible and scientifically very well received, but it basically cost too much. And so we exceeded the budget cap for that class of mission, and we weren't selected to build it. And that was 3 or 4 years ago. And then the next round, this was for what's called a medium class mission in the European Space Agency's program. And the next medium class mission opportunity came up, and it was suggested that we had another go and try to optimize the mission. A lot of the things that made the cost higher were risks that were associated with the lack of knowledge of how to do certain things. And of course, with the success of Hayabusa and other European programs, for example, studying heat shield materials for the re-entry capsule, it meant some of the high-risk things that we originally had were now not high-risk anymore and therefore were cheaper to do. And if we were very clever about the way we designed the satellite and picking the target, then we might be able to do a mission within the budget. And so that's what we're trying to do now. We've again been down selected to the last 4, and we're involved in the industrial study now, and I'll know in about a year's time whether we've managed to get the cost down far enough to have a chance for selection. But of course, we've got great missions we're competing with too, astronomy missions, so who knows? But if you're not in the game, you can't win. So I'm hoping that we will be the 3rd sample return mission. And what's exciting about Marco Polo R and OSIRIS-REx is that they are looking at a completely different scale of sample size. So rather than collecting milligrams, we're talking about collecting tens to hundreds of grams. Now, what this means is that we can do a whole range of more interesting experiments. Because we're going to a primitive object, we have a chance of detecting tiny dust grains, which we know are in meteorites, but there will be many, many more in more primitive material we can't sample on the Earth that predate the solar systems. These are grains that formed in the outer atmospheres of stars, survived in the interstellar medium and grew mantles of organic molecules in interstellar clouds and were incorporated into the early solar nebula and then into asteroidal material. So they can tell us about processes in the interstellar clouds. They can tell us even about what kind of star the material in the early solar system came from and whether there was more than one. But those things contain organic compounds. And one of the exciting things about asteroids is that they bombard the Earth, and they may have provided the organic material that seeded life on the Earth. And so it'll be very interesting to see if that organic material is present still in the asteroids. We're not talking about bugs in space, but we are talking about things as complicated as amino acids, which we find in these types of objects. So that material, of course, if you go to the surface of an asteroid and pick it up, it has to have been kept cool and not been exposed to ionizing radiation and sunlight and so on. So you need to be able to pick up large enough pebbles so the interiors of them are protected from the heating and the radiation and the atomic particles that are showering down on the surface of an asteroid. And of course, with 100 grams, you can pick up a large number of pebbles and get to their interiors and therefore study the organic molecules. With a large amount of material, you can do fantastic laboratory experiments with micrograms or even nanograms of material. But the thing is, you have to have the right microgram or nanogram. And you might need 10 grams of stuff to find the right one if you're looking for very rare particles. So by bringing 100 grams back, we can have many thousands of particles to pick from, and we might find those really esoteric, interesting ones which we've never seen before.
Mm. And have you chosen the target yet for Marco Polo R?
Yes, we have, and we've already changed it. This happens regularly with space missions, interplanetary missions, because there are often very specific launch windows that you have to launch into to keep the mass of the spacecraft down. Our target had to be a primitive asteroid, and we can tell things we think are primitive by observing their spectra from the Earth and identifying their characteristics and linking them to the spectra of meteorites that we have on the Earth. So we know certain types of asteroids are primitive. The difficulty is that they've got to be both primitive and dynamically very easy to get to, so the rocket doesn't have to be too big and therefore too expensive. And when you do that, you end up with a handful of objects that are possible, probably only 3 in fact, and they're probably the 3 that we're targeting. We were targeting Hayabusa 2 had already chosen one. It was the target that Marco Polo had. OSIRIS-REx had chosen one. It was the backup target for Marco Polo. And so we had to choose to go to something different. And we chose a rather more difficult object to get to, but the next most difficult, really, 1996 FG3. What was interesting about that is that it was a binary asteroid. So you basically got 2 asteroids for the price of 1. Binaries are believed to have formed from fission of asteroids by a process called the Yorp effect. And this is asteroids, believe it or not, can get spun up by the heat from the sun. When you heat a body, the photons that are leaving it from the heated part don't leave symmetrically from the body, because as on the Earth, the afternoon side of a body is always warmer than the morning side. And if it's not spherical, as those particles leave, they produce basically a tiny recoil force from the thermal photons leaving that can spin the body up or slow it down, depending on the direction of spin. And although it's a tiny, tiny force, over thousands and tens of thousands of years, it can spin up an asteroid so fast that it loses material. So you get migration of material from the poles to the equator, and then it's thrown off, and then it can re-aggregate and form a secondary. And all the characteristics of binary asteroids look like this is the mechanism. Now, what's exciting about that for sample return is that if you go to the poles of the asteroid, you're going to a place where the dust from the surface has basically been transported away to the equator, and so you can get to a surface that's relatively fresh and new, and therefore more likely to contain a larger proportion of pristine, unaltered, unweathered material, if you like. So this was what made our mission different from the other 2. And there's lots of interesting asteroid science you can do with a binary that you can't do with a single body. The problem was the mission was going to take 8.5 years, and that made it relatively expensive. But we didn't have a better target. Until very recently, we got some observations of an object called 2008 EV5, which is dynamically much easier to get to, and it turned out to be a primitive asteroid too, and probably even more interesting from its composition than the other targets, because it appears to have a higher amount of water content. That's not water that's free on the surface, it's locked up in minerals. But it does mean that it has a composition that looks almost exactly like the composition of the Sun, and therefore matches the composition of the early solar system much better than the other targets that we would have gone to.
You are listening to Under British Skies with Richie Jarvis, Nick Howes, Ian Melville, Paul Harper, Nick Evitts, Sam Hawkins and Jenny Winder.
Okay, that was a brilliant interview with Dr. Simon Green. I have one thing I want to add. Please, please, please contact the European Space Agency. Contact your local representative. Tell him you want Marco Polo R to run and you want NeoShield to be helped. It's a very, very important pair of projects, and that's all I'm going to say on the subject.
Absolutely, Nick. I mean, it's one of those things where if we don't start doing something about this now, then it's going to be too late. So
yeah, it is.
It's, by the time we actually discover something, that's not the time to start not panicking. That's not the time to start investing in this. The time to start doing it is now, so we're ready for it.
Yeah, the great thing is you can follow both missions on Facebook. NeoShield has a Facebook page, so does Marco Polo R, and so does the American counterpart to Marco Polo. So these are very, very important missions. We're looking at slightly different targets with Marco Polo R and its American counterpart. So they're worth doing. Even if they say, but the Americans are doing it, doesn't matter. There's a different target. We need both sets of results in order for us to really understand the solar system and how it evolved. So like I say, get the letters in there, get the emails in there, tell them you've heard about the mission, tell them you want it run as part of ESA.
Absolutely. We're really grateful to Dr. Simon Green there, talking to Ian. We have got some more of the interview with him a little bit later on. But before that, let's go back to Ian talking to Dr. Simon Green and hear what else he had to say. And after that,
we'll get to hear from our own Astro Jenny.
Yeah. So she just spoke about ESA, didn't she?
And there's an article on space for the cost of a movie ticket.
Yeah.
All important stuff.
Yeah.
Right, so we've talked about Giotto and Stardust and IRAS and Marco Polo R, of course. You're also working on NeoShield?
Yes, this is not a single mission yet. This is a project that's actually funded by the European Union, and it represents a particular stage in a process that I can sort of tongue-in-cheek say is my part in saving the world from disaster. It's looking at ways in which we can prevent an asteroid from hitting the Earth. Now, this sort of event is obviously extremely rare for the sort of thing that could cause global disaster, something the order the size of the asteroid that caused or is believed to have caused the extinction of the dinosaurs. What we know for sure is that the Earth is hit at regular intervals by large asteroids. The average time between those impacts is of the order of 50 to a few hundred million years. But that's for objects a few kilometers in size that can basically, wipe out a significant fraction of all the species on the Earth, and has done several times. But as you go for smaller bodies, the amount of damage gets lower, but of course the number of bodies is larger, and therefore the frequency with which these impacts occur gets larger. And you can look at the really big things. They're easy to observe, and we now believe everything larger than a kilometre in size, we probably know of the orbits of 90% of them. And none of those objects are going to hit us in the near future. By near future, I mean however far ahead that the dynamical models can predict, not for thousands of years. But there may be only 1,000 objects bigger than a kilometre that could hit the Earth, but there are about 100,000 that are bigger than, say, 150 metres. And 150 metres is the size at which we still think that we should be trying to stop an impact. Because something 150 metres hitting ground can produce a crater that may be a kilometre across and will cause damage over a much larger area than that. So if something like that hits the centre of London, you're really talking about, 20 million casualties instantly, and a significant number after that from the effects of the impact. If it lands in the ocean, you can produce a tsunami, which could do even more damage if it was near a low-lying coastal area. So of those 100,000 objects that might do that, we know of a few thousand only. So we've only got a few percent of the way to discovering them. And there are big programs with telescopes dedicated to searching for these things, and we're finding them at quite a high rate. Once you find them, you calculate their orbit, and you then determine whether they have a chance of hitting or not. And of course, if you discover they do have a chance of hitting, then you start worrying. People observe the objects more, and if that probability gets down relatively low, then given our ability to launch spacecraft and our ability to do fantastic things in space, wouldn't we be foolish if we didn't have trick up our sleeve to stop one of these things hitting if we could? And so that's what NeoShield is about. It's designed to basically take the next step in the design and understanding potential efficiency of different design concepts to stop asteroids from hitting the Earth. There are two really distinct methods that are thought feasible and tractable at the moment. Within Europe, the tendency is to go for something called a kinetic impactor, where you launch a spacecraft that hits the asteroid, And although the spacecraft has a tiny mass compared with the asteroid, it's traveling at relatively high speed, 10 kilometers a second, and it transfers momentum to the asteroid and moves it a tiny amount in its orbit. But if you can do it early enough, a small deflection a long time before can result in a change in position that's bigger than the radius of the Earth, and therefore something predicted to hit the Earth would miss it. Significant amount before, we're talking about years, maybe decades preferably. The second mechanism, which is one favoured in the US, is something called a gravity tractor. And the nice thing about this is that you don't have to know anything about the properties of the asteroid because you don't touch it. You basically launch your spacecraft, park it near the asteroid, and then you fire your rockets very gently. And even though the spacecraft has a very small gravity compared with the asteroid, it does exert a gravitational pull on the asteroid in the same way the asteroid does on the spacecraft. And so you use its tiny gravity and the thrusters to basically pull the asteroid out of the way. It's astonishing that it will work, but if you have long enough, 20 years or so, it will, so long as your asteroid isn't too big. So if you have something that's maybe 100 to 300 or 400 meters in size, the gravity tractor will probably work. But you need 20 years or more warning to use that method. So if you've only got a very short warning time and the asteroid is very big, neither of those methods will work.
And you just panic.
So you resort to Bruce Willis style. Well, you don't blow it up because that would just lots of fragments that hit you instead of one. But what you do is you use what we call blast deflection. So you create an explosion close to it that releases a large amount of energy which heats the surface up, vaporizes part of it, and the jet effect of that vaporization pushes the asteroid away. Now, if you use nuclear weapons, you can get a very large effect, and therefore you can do the deflection much later than you could with a kinetic impact or a gravity tractor. The problems with this are rather obvious. Nobody wants to be testing nuclear weapons in space.
Yes.
Never be able to test it. It will always be a last resort. It has to be there on the books as a possibility, so it's one of the things we're studying too.
Mm.
And then the other thing is, how small do you go? Because things that are on the threshold for survival into the atmosphere, 50 to 100 meters, would do a relatively small amount of damage. I mean, they could destroy a town, but it would be cheaper to evacuate the town and let it happen. It would be to send a spacecraft and stop it.
Mm.
And so there, your option is civil defense. And you have to make the decision, at what point do you decide, right, we're going to sacrifice a town and set in train the process of evacuating maybe, a few tens of thousands of people, and then tell them afterwards, oh, well, actually it missed after all.
Well,
Which isn't to do with science, but of course it requires an understanding of the scientific principles in order to set a mechanism up to make the right decision.
and that's what the Torino scale's for, I suppose.
The Torino scale essentially looks at two aspects: how big the object is, in other words, how dangerous it is, and what the impact will be. So something that is very big and has a high probability of impact gets a very big score on the Torino scale, because you really want to do something about it. If you have a very high probability of impact but no danger, then you get a moderate score because you're less concerned about the fact that it's going to hit. Almost every object that we discover never makes it onto that because the probability is still low when it essentially is determined that it's going to miss and it goes to zero. In a way, I sort of feel a bit cheated because every time I go to international conferences on asteroids and I talk to my colleagues who study this subject, and we always bemoan, like all scientists do, there's never enough money available to study our pet subject. What would we like to happen to suddenly increase our funding? And of course, what we'd like to happen is to be hit by something big enough to make everybody take notice, but small enough to not do too much damage, with an object big enough to make a few 100 meter sized crater. And we always end up with it landing in Australia because it's a politically safe country with vast areas with no people. But you can go and look in the hole in the ground. So politicians can go there and look and think, wow.
We've talked about space missions, we've talked about asteroids and sample returns. Let's just talk a little bit about how you started out in astronomy.
I don't know the moment when I decided that's what I wanted to do. When I know it was when I was at primary school, and it's the sort of time when everybody wants to be an astronaut or maybe something more mundane like a fireman or a policeman or
train driver.
Train driver, yes, that's another one, yeah. And I remember I wanted to be a marine biologist. I remember watching Jacques Cousteau on television and thinking, wow, that looks like a really great way to earn a living. I want to be a marine biologist. And then something happened. I don't know exactly what it was, and it made me look up at the sky and for something. I honestly don't remember what it was now, and just think, wow, I'm seeing things that are so far away that I'm seeing back in time, and just the vastness of the universe was kind of fascinating. And I suddenly switched my allegiance to being an astronomer. And of course, most people who do that, they grow out of it, and I didn't really. I just kept being interested. I got to the end of my schooling, had to choose a subject to study at university. At that time, I had the luxury of not having to worry about what job I would do. I just had to pick a subject that made you employable. So physics was the ideal thing, but actually I was rather bored by physics. But I would study physics and do astronomy. That's great. So I did an astronomy degree. And then I got to the end of my degree and I had to face the real world of jobs and thought, don't fancy that either. I'll try a PhD. And I was lucky enough to get a PhD place, and then lucky enough to get a research place, and then lucky enough to get a lectureship. And, I've avoided that really hard decision about how to spend my life. I've just kept doing astronomy, and it's just been fantastic, I have to say.
Well, you're a very lucky man. But didn't Patrick Moore give you some advice at one point?
He did, yes. Well, actually, at that time, I lived on the south coast, relatively close to him, and he used to organise events, and the local societies used to organise events he came to, and so I ended up with a whole bunch of astronomers at his house to look at his telescopes. And so I asked him, I was halfway through O-levels at the time, I think, and I asked him, about advice about what university course to do. And he said, if you're 99.9% sure that you want to do astronomy, then study physics. You have to be 99.99999% sure to do astronomy. And so I ignored his advice and did astronomy. And that was one of the few places that did a pure astronomy degree. There is nowhere anymore that does that. They all very wisely combine it with physics. So I missed some of the important physics that would have made me more employable in industry perhaps, but I've fortunately not had to face that. Nowadays, astrophysics is studied and astronomy is studied at a large number of universities, but jointly with physics. And they're among the most employable people in the country. So there are very few astronomy jobs, so it has to be that way. But, I think a lot of people are attracted to the subject because it's exciting, but they know that they're going to be very employable at the end because of the wide diversity of skills they have and problem solving that they have. Employers that have nothing to do with science even are still like astronomers.
It's a good grounding in science and mathematics. Well, I think that just about wraps it up. I'd just like to say a very big thank you to you, Simon, for joining us this evening. It's been an absolute pleasure.
A pleasure for me too.
Thanks very much.
Okay, bye-bye.
Next, we have our very own Astra Jenny, and she's talking about space for the cost of a movie ticket.
Later this week, the European Space Agency will be holding a meeting in Naples to discuss its plans for the future. And this seems a good time to reflect on the almost 40 years that ESA has served as Europe's gateway to space. After the Second World War, many scientists and engineers went to work in America or Russia, leaving individual European nations unable to compete in the race for space between the two superpowers. In 1975, 10 European nations formed the European Space Agency to provide and promote for exclusively peaceful scientific purposes cooperation among European states in space research, technology and applications. Today, their mission to develop our space capabilities continues to bring both scientific and economic benefits to both Europe and the world. Its programs are designed to study Earth, its immediate space environment, our solar system and the universe, and to develop satellite-based technologies and services and to promote European industries. There are now 20 member states representing 500 million citizens, as well as other cooperating countries that come together in their national interest and for the common good. It employs around 2,200 personnel from around Europe, including scientists, engineers, IT specialists and admin staff, who work in a culture of diversity, collaboration and excellence. They also mount joint missions with other international agencies, including NASA and the Japanese and Russian space programs. ESA stands as one of the world's leading space agencies, active in all areas from space exploration and scientific research to weather satellites, space-based telecommunications, navigation and environmental monitoring. Yet it does all this on a budget several times lower than any of its international counterparts. Their budget for this year is €4,020 million. Divided between the 500 million European citizens, this amounts to around €8 per person per year, about the cost of a cinema ticket. Despite this modest budget, ESA has mounted some audacious missions. When it was founded in 1975, it launched the COS-B satellite to monitor gamma-ray emissions in the universe. In a joint mission with NASA in 1978, it launched the International Ultraviolet Explorer, the world's first high-orbit telescope. In 1986, ESA's first deep space mission Giotto studied comets Halley and Grigg-Skellerup. In 2003, Mars Express became the first fully European mission to any planet. Joint missions with NASA include the solar missions SOHO and Ulysses and the Hubble Space Telescope, while ESA's Huygens probe travelled to Saturn with Cassini to become the first probe to land on a world in the outer solar system when it touched down on Titan in 2005. In 2008, ESA's Columbus laboratory was added to the International Space Station, and in 2009, ESA astronaut Frank DeWin became the first European commander of an ISS expedition. That same year saw the launch of the Herschel and Planck missions. ESA is currently developing a series of next-generation Earth-observing missions, the Sentinels and Earth Explorers. The Gaia mission to survey 1 billion stars and create a 3D map of our galaxy will launch next year, and the Bepi-Colombo mission to Mercury is due to launch in 2015. ESA is also keen to develop a more sustainable future in space. Its Clean Space programme addresses the environmental impact of all aspects of their missions, from concept development through to the end of a mission's life, looking at ways to consume less energy with greener methods of propulsion, use more eco-friendly and sustainable materials, produce less waste by cutting levels of space debris and bringing down costs. One answer is to use CubeSats, small, low-cost modular nanosatellites that measure 10 centimetres a side with a mass of about 1 kilogram. These can be used for specialised missions that can be developed cheaply and quickly to respond to rapid advances in scientific research. The future for Europe in space is looking bright and well worth the cost of a cinematic.
So it's a bit unfortunate that this month we don't have an app to actually look at, and also a book as well, but we do have a few in the pipeline that we're going to look at. But if you do hear of any astronomy apps or anything that you think would be good to pass on to everybody else, please get in touch at ubs@astronomy.fm. We'd love to hear from you.
Out of interest, Richie, next month on the Sky at Night, it will be talking about Mercury and the Moon, so that should be a very interesting show for quite a few astronomers interested both in the planets and, of course, our satellite, the Moon.
Wow, that will be pretty good.
And, of course, hopefully there'll be more stuff coming to light from the Messenger missions too. So if you're in the UK, do tune in to the Sky at Night, and you're guaranteed a very good astronomy show, that's for sure.
Brilliant. I look forward to seeing that. Right, so now it's pretty much the end of the show, I guess.
Ooh.
So
I'd like to thank everybody for listening to us on Under British Skies. This is Nicky Vetts.
This is Richard Jarvis. Thanks for listening to us this evening, and we'll see you again next month.
You have been listening to Under British Skies with Richie Jarvis, Nick Howes, Ian Melville, Paul Harper, Nick Evitts, Sam Hawkins and Jenny Winder. The show is engineered by Michael Forster and produced by the team. Under British Skies is broadcast live on astronomy.fm radio on the third Sunday of each month at 8 p.m. GMT. You can contact the team on Twitter at Under British Sky or email us at ubs@astronomy.fm. See you next month.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are astronomy.fm. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is astronomy.fm radio.
AFM.